So the first thing, problem set number 6 is due the day of the exam. So this quiz question will not cover anything on example 5 or 6. It's going to be stuff that we've already covered in this, thoroughly in these discussions that we're doing. Yeah, exam is on lectures 1 through 6. I know I had 7 there initially, but I combined 6 and 7 together. So quiz on Monday. So that means most of the problems you should be able to solve now. The ones I'm doing are the trickiest ones on the homework. And I think example 6.5, the one that we just did right here, is a tricky problem. It's hard. This is a problem that really brings in Newton's third law in a very sophisticated way. So here we go. So you got a slab, which is the green slab, and you can see that it's more massive than the red block, which is M1. Block 1 is at rest, but there's a force applied to block 1. And really the key point here is, look, there's friction between block 1 and block 2, and there's no friction between block 2 and the ground. That is really important here. So there's no friction between block 2 and the ground. So what does that mean? If you apply a force on block 1 is going to force by friction, Newton's third law, to pull both of them. So what this means here is that we expect acceleration for the system of block 1 and 2, because there's no friction there. But the question is this: does the block 1 accelerate over block 2? Does block 1 accelerate on top of block 2? And again, talking about free body diagrams like we were talking about before, we can immediately ask the question of, from what we talked about before, if the force of F acting on block 1 is greater than the static friction, it's going to accelerate. So in other words, when I look at this thing, I have my block. Let's go draw my block. So here's my block, right? And now I have a surface here. And the surface in this case is that of this guy here. So when I'm looking at, So when I'm looking at this guy on block 1, there is a force acting on this block in this direction. And of course, there's friction between block 1 and block 2. So when I look at this guy, there's a frictional force like this. So here's the question that we're asking here is, if F is greater than this, and it's greater than the max value, then this tells us here is that block 1 accelerates over block 2. However, if the force is less than static friction, then we can say here is that block 1 stays at rest. And therefore, that's the static friction is really the force that's going to make the block the system 1, 2 accelerate? Okay, so let's go look at this thing here. So the first thing that I'm going to do here is that we already know that the system 1, 2 must accelerate. So the question is, what about block 1? That's what we want to focus on. So here we go. So the first thing I'm going to do here is that I'm going to draw my system. So I'm going to focus on block 1. So here I go. So I have the ground, right? And on top of the ground here, I got a block. Here's my block or my slab. And so when I'm looking at the slab here, I know that I have my block here that's experiencing a force. So when I'm looking at this guy, what am I seeing here? Well, I'm going to draw my free body diagram, and I know that this is 2, this is 1, but we're only focusing on 1 right here. So here we go. I know that there's going to be 2 forces here vertically. There has to be the normal force of 1. There has to be the gravitational force of 1 down. And now I have 2 horizontal forces. One is F and one is static friction. But remember, when I'm thinking about static friction, I'm going to call that F of S of 1 because we're talking about block 1 here. So this guy's got to be mu S times the normal 1. So my assumption here for right now is I'm going to assume that this thing actually moves. So the only reason I do that is that now I can set my plus and minus signs. So let's go write down the equations here. Okay, so we're checking here. We need to check if F, which is 100 newtons, is either greater or smaller than Fs of 1. So let's go calculate Fs of 1. So when I look at this thing, you can see that I need this here, right? So when I'm looking here for block 1, then I know that this guy's going to be positive F minus the frictional force. And we want to know if this thing is greater or not. And then if I look at the forces, by the way, that was in the X, this is in the Y. Of course, this means positive N1 minus M1G. And we know this has to be 0. So this immediately tells us that N1, of course, has to be M1G. So here's the question, right? What is it? Is it this or is it that? So let's go answer this question here. So I need to determine this guy here. So the frictional force Fs1 is then going to be mu of S times the normal 1, which is going to be mu of S times M1G. So if I plug in my values here, this is going to read, what's the friction? So the static friction is 0.4 times the mass. This is 10 kilograms times G, 9.81. And if I compute that, it becomes around 40 newtons. So this implies here is that the force F is greater than this. So therefore, block 1 accelerates over the slab or block 2. So we know it accelerates. So look what this means here. If it accelerates, that means mu of S changes to mu of K, And mu of k in this situation is 0.4. Oh, is it 0.4? Oh man, am I messing up with my numbers again? Oh man, look at that. Static friction is 0.6. I screwed up. This thing should have been 0.6. So this guy should have been around 60. But 60 is still less than 100, right? This is 100 newtons. This is around 60. So it is greater than that. Okay, sorry for the numerical errors today. So now we know that it's sliding. So what am I going to do? I got to write down my newtons. So now that means that we know it's accelerating. So here I go. So now we have an accelerating block. So now what I'm going to do here is that I'm going to rewrite the N2L equations here. And so here I go. So the sum of the forces in the x direction then is going to be what? It's going to be positive F. But this time, remember, I got to change it to kinetic friction. So this thing's going to be minus mu of k times m1g. And this is going to be equal to which mass is being accelerated? m1a. Okay, so then we already know the y portion, which was positive n1 minus m1g. And of course, this is static. So now that I have that, the main equation is which one? Is this guy right here. This is the one that we want to pay attention to. But all of Newton's second law here is right here. So what do I need to do? I need to go in and I need to calculate the acceleration of the block. Let's see, how much time do I have? I have just a little bit more here. So now we can calculate the acceleration. So if I do that, you could see here that if I isolate A, I just got to divide this quantity divided by the mass of 1. Look at that. I dropped the mass. No, I didn't. It's right there. So here I go. I know that F is 100 newtons. I know that mu of K is 0.4. And I know that M1 is 10 kilograms. So if I plug everything into here, I get an acceleration of 6.1 meters per second squared. I now know the acceleration of this block. So now that I know the acceleration of this block, the bottom line here is that I need the acceleration of the slab. So that's what we're getting. So now the next thing that we really want to pay attention to here is that we then want to ask, does the slab, what is the slab's acceleration? So let's go look at that. Now, no, I know that this is language, but you got to be careful with language. And so let's draw our blocks here. So what I'm going to do here, where's my mouse at? So let's draw a picture here. So what is the acceleration of the block? So for starters here, we have a surface. And we know that this surface here is frictionless. So now I have my block. And when I'm thinking about my block here, the thing that I'm going to think about here is that I'm going to think about what? I'm going to think about this guy. So here's my slab. Now, there is the other block on top of it, and I know that it's really common for people to sort of like draw this slightly different. And so I'm going to talk about it being different here. So this is, of course, 1, and this is, of course, 2. So what do I see here? What I'm really focused on is on the slab. We know for a fact that this guy's going to accelerate. Why? Because the friction coefficient is 0. So when I'm looking at this, so I want to be real careful on how I draw this. Well, we know that M2 has to have what? It has to have weight. And then there's the ground here. So when I'm thinking about the ground, I'm thinking, well, there's the normal of the ground acting on this thing here. But what about block 1? It's very common for people to come in and say, that's the weight. Well, it's actually not the weight, it's the normal. It's the normal. It's applying a surface force on block 2. It's not the weight. Now, we may be saying, well, mathematically it turns out to be the weight, but at least get the language right. This is a contact force, so block 1 is applying a normal force onto that. Now remember, which direction was the friction on 1? So when you look at the friction, it's in the opposite direction. So that means here that the friction in this case has to be where? It has to be in the forward direction by Newton's third law. So this is the kinetic friction.
Can you elaborate a little bit more on how to determine the direction of the frictional force?
Sure. How about if we
Let's
draw a second picture first. So what I want to do here is that I want to look at the green block. So if I look at the green block, and you could see here that I have that scenario right here. Now let's go in and draw block number 1. Okay, and so this is block number 1. So we agree that this is 2, this is 1. Now, which direction was, so when we were looking at block 1, we saw that there was a force F. And which direction was the force F doing? It was being moved to the left. So let's look at this thing. So as the force is being applied in this direction here, look at what the green is doing to the purple. The green force is going to apply a force in that direction. So this is going to be the kinetic friction of the green on the purple. But wait a minute. Because I have peaks interacting, that purple must then be applying a force in this direction by Newton's third law. So you're seeing 2 peaks interacting, one's applying a force to the left, and then the other one has to be applying a force to the right. So therefore, they have to balance each other out according to Newton's third law.
Is it dependent on if the system's moving or not that you decide the direction?
It does not matter whether the system is moving or not.
Or accelerating?
Yeah, because what you're seeing here is that let me do this peak here. And let me do this peak here. So let me do it in the other direction. So you could imagine that there's this peak right here. The purple is trying to go in this direction. Why? Because the force is going in that direction. So what is the green peak doing? It's stopping it. So it applies a frictional force in that direction.
Mm-hmm.
But now there is no red force. I'm only focusing on the green. So this is when we were focusing on that. So now if we focus only on the green slab, what you're seeing here is that now I have
the green slab here. And what you're seeing here is that purple now is acting on what? The green slab.
So it goes in the opposite direction to the motion, or?
Yeah, because according to any kind of contact, it has to go equal and opposite. And
But
this,
then the static friction goes
this
also
isn't
opposite,
static
or?
friction right now,
Yeah, this
right? This is kinetic
kinetic.
friction.
Yeah.
And that's because this block is accelerating, so it's sliding. So if I'm focused on the purple here, maybe I should have done this a little bit more clearer. How about if I do this a little bit different? And maybe that might help.
I guess there's a general rule of thumb of deciding the direction of the static and kinetic frictions.
I think you have to look at this guy right here.
Right. It's dependent on what you're looking at, basically,
Right. And
right?
here, what we're doing here is that we focus only on the purple block.
And so kinetic friction happens at the point once, or like you say, or is it terminal velocity or?
No, it's the point, the breaking point.
The breaking point, that was so, and then before the breaking point, it's in static friction?
It's in static friction. So it's a variable force.
Right. And then that direction, the static friction, is that in the same direction as the object, or?
No,
Opposite
static
motion?
friction is going to be in the opposite tendency of the object to move.
Opposite tendency. So the tendency for this object is to move left or down?
Yes, it is moving left. We know
It
that
is
for a
moving.
fact because that's
Right.
the first thing we checked.
Right. Okay, got it.
So as that purple is trying to slide, you could see that the frictional force of the green and the force of the red it's a battle between those two. But we
Right.
now know that this guy is longer.
Longer.
But here, now it's not about the purple, it's only about the green. So what's acting on top? There's nothing at the bottom because it's frictionless, right? This implies frictionless. So the only force acting on the green has to be a peak of the purple. And the peak of the purple is doing what? It's moving it there. So it's really Newton's third law where you have equal and opposite frictions.
And if the ground wasn't frictionless, would we be applying another kinetic friction
Yes,
force?
it would be another kinetic frictional term.
Okay, got it.
Okay.
I have a
So
question.
then if I go draw, by the way, great questions. If I go and I draw a free body diagram of the situation, right? It's got to be this here. It's got to be like this. Hold on a second. Nope, that's my cat, unfortunately. Sorry about that. We got 2 dogs and a cat. So, or actually 2 dogs and 2 cats. Okay, so here we go. So now, if I look at this thing here, now my free body diagram tells me that it has to look like this. So I have my normal. And then I really have a second normal, which is the contact between block 1 and 2. That's what we call a surface force. And because this thing is perpendicular, it's a normal force. It's a surface force. Gravity is not in contact with, right? The force of gravity on block 1 plays no part on block 2. But the force of gravity does play a role on the slab. So then when I look at this thing, you could see here is that now I have kinetic friction, which is equal to this guy right here. And this guy is, of course, moving in this direction. and we know that it's accelerating in that direction. So therefore, that's positive, negative, positive, negative. So now I'm going to go write the equations here. So if I now write the N2L equations, what do I write? What I write here is that I could see here that I have an unbalanced force in the x direction for the slab. You know, maybe I should be a little bit more careful, and I should say this is for slab 2 or block 2. And so you could see here that this is the frictional force, and which is of course mu k times the normal 1, and that has to be, I'm sorry, I wrote 1, it should have been 2. And this has to be the mass of 2 times the acceleration of 2. And
Is it not
then,
negative, or
say that again?
or are you not counting the? I guess like I would make it negative, but maybe that's just how I write it, just in my coordinate system.
Yeah, I just, whatever the motion is,
Oh, I see.
I make that positive.
I get you.
Yeah, just like when you drive to Santa Cruz or you drive back from Santa Cruz, I'm assuming you're not calling that positive and that negative.
Right. Okay. Okay.
Yeah, by the way, textbooks really kind of force you to make that left negative. But then you carry all these funky minus signs. So then if I look at the second one, you could see that I get positive N2 minus N1 minus M2G. And then that has to be in static equilibrium. So we're seeing here that I now have these equations here. And one of the things that we're seeing here is that there's a couple of things that we can talk about. First of all, do I know what the frictional force F of K is? Yes. Why do we know what the frictional force is? Is because we calculated that already.
Wait, and
Right?
why can we say this? Why can we say these equations? Like, why can we say that the sum of the vertical forces equals 0?
Because the slab is not moving along the y direction.
Only
It's
x.
stationary. So this guy right here is in static equilibrium.
But in the horizontal, it's not.
Right. And this is accelerating, right? It's speeding up.
So anytime
Horizontally.
we are speeding up, our sum of the forces equals ma, essentially.
Right. That's the effect.
Right. Versus a
Right? The
static.
cause is the net force, and this is the effect here.
Cool.
And so the thing about it is that there's multiple ways to do this problem. Okay. So from Newton's third law, the frictional force is equal and opposite for both blocks. So I could come in here and just say, you know what? For block 1, I know that's the case right there. I could calculate the force this way, which doesn't involve block 2 at all. And if I do this, I could come in and I could just, go in here and I can write 10 kilograms, of course, and 9.81 meters per second squared. I actually did not calculate this number in my calculator. Let me punch this in real quick. So this is so I get 39.2. So this would be 39.2 newtons. And that's a totally legit way to do that. Or we could say that from N to L, we solve for the frictional force. And what I mean by that, if you look at this from equation 4, we could see here that N2 must be equal to N1 plus M2G, but we know from the previous example that that normal is M1G. So therefore, this is really M1 plus M2G. Now that I have the normal, I could then use equation 3, which then says here that then mu of k times the normal 2 is going to be mass of 2 times the acceleration of 2. So in that case, you could see that I'm getting this guy, but I'm using a different mass. So if I so in this case, we could have just said, okay, the frictional force we know is 39.2 newtons, and this is really M2 times A. And then I could get my acceleration, and if you solve this for the acceleration 2, I could then go in and I could calculate the acceleration, which in this case, it turns out to be 0.98 meters per second. So that's a totally way to do the acceleration, or I could do it this way, which is different. But they lead to the same answers.